Hello student, welcome to your chemistry lab. Today I am discussing chemical bonding. Here I will be discussing second part of chemical bonding, that is covalent bond and formal charge. It is important for JEE and NEET and also board, so read very carefully. So now we are watching the whiteboard. Covalent character of ionic bonds. Every ionic bonds contain a mixture of covalent and ionic character. Generally, a compound is ionic or covalent as long as compound in question is predominantly one or other. In many cases, however, it is convenient to be able to say something about intermediate situation. In general, there are two ways of treating ionic covalent bonding. The method that has proved most successfully is to consider the bond to be covalent and then consider the effect of increasing charge displacement from one atom towards another. Another method is to consider the bond to be ionic and then allow the certain amount of covalency to occur. The second method was due to Fajan's rule. This theory has found no place in repertoire of the theoretical chemist, largely because it has not proved amenable to the quantitative calculation which other theories have developed. Even then, the qualitative idea of embodied in the Fajan's rule offers simple, if not exact, approaches to the problem of partial covalent character in ionic compounds. Fajan's considered the effect which a small highly charged cation would have on anion. If the anion were large and soft enough, the cation should be capable of polarizing it, and the extreme of this situation would be cation actually penetrating the anionic electron cloud given a covalent shared electron. Covalent means shared electron, and this is the structure. Fajan suggests that the following rules to estimate the extent to each of cation could polarize an anion, and this is the induced covalent character. Polarization effect of structure A, idealized ion pair with no polarization. Structure B, mutual polarization pair, and structure C, polarization sufficient to form covalent bond, and dashed line represent hypothetical unpolarized ion. Fajan's rule. First point, small cation with more charge. Small highly charged cation exert a greater effect in polarizing anion than large and or singly charged cation. Thus, in the group of periodic table, down the group ionic character increases with a particular anion. Example, the order of covalent character of alkali metal chlorides like LiCl is more NaCl than KCl than RbCl than CgCl. Similarly, in the period from left to right, covalent character increases for the metal ion with a particular anion, that is LiCl is less than BeCl2 less than BCl3 less than CCl4. Point 2. Larger the anion with more charge, the polarizability of the anion will be related to its softness, that is to the deformability of the electron cloud. Both increasing charge and increasing size will cause this cloud to be less under the influence of the nuclear charge of the anion and more easily influenced by the charge on the cation. Thus, the order of covalent character of halide with a particular metal is in the order NaF less than NaCl less than NaBr less than Na, and in a period of the order of covalent character of the compound left to right will be order Mg3N2 greater than MgO greater than MgF2. Point 3. Electronic configuration of the cation. Cation with inert gas electronic configuration form ionic compounds, while those cation with pseudo inert gas configuration favor the covalent bond formation, and the cation with pseudo inert gas configuration due to the poor shielding effect of d electron have more polarizing power on anion and thus considerable more covalent those of cation with inert gas configuration. For example, ZnCl2 is more covalent than CaCl2. Similarly, compound like CdCl2, HgCl2, Cu2Cl2, AgCl have covalent character. Lattice enthalpy, the energy given off when gaseous positive and negative ions comes together to form 1 mole of the solid ionic compound is called lattice enthalpy, that is denoted by U, capital U. For example, Na plus and Cl minus form NaCl solid, that is del H equals to minus del U, and reverse process NaCl solid decomposes Na plus and Cl minus del H equals to plus del U. Lattice enthalpy varies directly with the charge of the ion and inversely with the size of the ion. Thus, lattice enthalpy directly proportional to charge of ion and inversely proportional to size of ion. Lattice energy can be calculated using Born-Haber cycle. Born-Haber cycle. In 1919, Born and Haber devised a cycle for the calculation of lattice energy. The calculate heat of formation of sodium chloride, that is heat of reaction. Here this is Na sodium solid react with Cl2 gas gives NaCl, that is del HF equals of NaCl, del HF of NaCl. Sodium solid, Na solid converted to sodium gas, Nag, that is del H sublimation, means sublimation energy, and Na gas converted to Na plus ion, that is ionization energy. And next half Cl2 means Cl2 gas converted to Cl, that is the dissociation energy, and Cl gas converted to Cl ion, that is Cl negative, that is electron affinity, and two ions come together form a NaCl solid, that is the lattice energy. Here electron affinity is negative and lattice energy is negative, and we see that Na sodium and Cl2 gas, that is the del H formation, equals to NaCl solid. All the above energy factors are interrelated in Born-Haber cycle, which can be summarized in figure. Del HF equals to means total enthalpy of formation, that is del HF equals to del H sublimation plus half into del H dissociation plus ionization energy minus electron affinity minus lattice enthalpy. Covalent bonding. A covalent bond is formed between atoms of comparable electronegativity. The attractive force are developed due to the sharing of electron pair, with each atom contributing one electron to the pair. Covalent bond may be defined as a force holding together atom through sharing electrons. First, here hydrogen. Hydrogen have one electron and two hydrogen form HH bond. This is the covalent bond. Here one electron of each atom are sharing and form a single bond. Chlorine have 7 electrons. One electron of chlorine of each atom sharing form a single bond, and oxygen have 6 electrons and form double bond. Here oxygen sharing 2 electrons of each atom form double bond, and for nitrogen sharing of each atom, 3 electrons are sharing, form a triple bond. Covalency. It is defined as the number of electrons contributed by an atom of the element for sharing with other atom as to achieve the noble gas configuration. It can also be defined as the number of covalent bond formed by the atom of the element with other atom. The usual covalency of an element except hydrogen, which has covalency is 1, is equal to 8 minus number of group to which an element belongs. This is true for the element belong to 14, 15, 16 and 17 group. This is the stable. Carbon belongs to group 14, so 8 minus 4 equals to 4, that is the covalence equals to 4. Silicon also in group 14, so 8 minus 4 equals to 4. Nitrogen belongs to group 15, so 8 minus 5 equals to 3, covalence is 1, and similar for all cases. Characteristic of covalent compounds. Physical state. In covalent compounds, molecules are held together by weak van der Waals forces of the attraction, and that is why covalent compounds are found in all three states, that is solid, liquid or gaseous state, and tendency to become solid increases with increase in molecular weight. Melting point and boiling points. Generally, covalent compounds have low melting points and boiling points due to weak attractive force between the covalent molecules. The low melting point and boiling points of the covalent compounds are due to the break of weak dispersion force between the molecules, not covalent bonds between the atom within the molecules. Giant covalent molecules like silica, diamond, etc. are very hard and have very high melting points and boiling points, because in such cases the covalent bonds have to be broken and extended three-dimensionally. Point 3. Isomerism. Covalent bonds are rigid and directional, and hence the covalent compounds exhibit stereoisomerism. Point 4. Solubility. Generally, covalent compounds, mainly non-polar, are insoluble in water but soluble in organic solvent. Some polar covalent compounds are water soluble due to hydrogen bonding but insoluble in non-polar organic solvent like benzene, example sugar in water. Point 5. Electrical conductivity. Covalent compounds are non-conductors because they do not contain mobile ions or free electrons. Point 6. Chemical reaction. In their chemical reaction, covalent molecules undergo molecular reaction. During the reaction, bond breaking and bond making take place. Therefore, these reactions are generally slow and rarely proceed to completion. Limitation of Lewis concept. First point, it could not explain bond energies and bond length. Point 2, it could not explain the geometry and shape of the molecules. Point 3, it could not explain how the molecules having expanded octet and the molecules with the incomplete octet are formed and stable. It will be discussed, that is the Lewis concept discussed in previous class, that is chemical bonding part 1. Polarization of covalent bonds. If a covalent bond is formed between two atoms with same electronegativity, the shared pair of electron is shared equally by the two bonded atoms, and the bond is said to be non-polar as in case of hydrogen molecules, that is H2. However, if the covalent bond is formed between two atoms with different electronegativities, the shared paired electron will be attracted more towards the more electronegative atoms. As a result, the more electronegative atoms acquires a partial negative charge and the less electronegative atoms acquires a partial positive charge. in case of HF. Hydrogen have delta positive and fluorine have delta negative. Means hydrogen have partial positive charge and fluorine have partial negative charge. The bond is now called polar bond. It means that covalent bonds may have some ionic character, like an ionic compounds or ionic bonds may have some covalent character. This is discussed in terms of polarization. When two oppositely charged ions come closer to each other due to attraction of electron charge cloud of the anion by the positive charge of the cation, the electron charge cloud get deformed and distorted or polarized towards the cation. This phenomenon of distortion of an anion in approach to cation in term polarization. The ability of a cation to polarize an anion is termed as its polarizing power or polarizing ability, while the ability of an anion to get polarized by a cation is called its polarizability. It should be noted that an anion can also be polarized a cation, but due to small size of cation, the extent of polarization is too small and to be significant. This can be illustrated with the more extent of polarization. The more is the stability of the bond. The factors affecting the extent of polarization are given here. Point 1. Size of cation. Smaller the size of the cation, more is the charge density and greater is extent of polarization. This means that cation with small size have high polarizing power. Point 2. Magnitude of positive charge. Higher the positive charge on the cation, stronger is its attraction for the electron charge cloud of the anion. Greater is the extent of polarization. This means that cation with high positive charge have high polarizing power. Point 3. Electronic configuration of the cation. Due to poor shielding effect of d electron, cation with pseudo noble gas configuration, that is NH2NP6 N-1 D10, have greater effective nuclear charge as compared to the cation with noble gas configuration NH2NP6. As a result, cation with pseudo noble gas configuration have high polarizing power. Point 4. Size of anion. Larger the size of anion, easier is the distortion of its electron charge cloud and more is its polarizability. This means that anions with large size are easily polarizable. Point 5. Magnitude of negative charge. Higher negative charge on an anion, easier is the distortion of its electron charge cloud and more is polarizability. This means that anions with high magnitude of negatively charged are more polarizable. This can be summarized in terms of Fajans rule as smaller cation, larger anion, more charge on the anion, and greater is the polarization and more is the covalent character of a bond. Formal charge. Lewis diagram in general do not represent the actual shape of the molecules. In case of polyatomic ions, the net charge is perceived by the anion as a whole and not in a particular atom. It is, however, feasible to assign a formal charge on each atom. Formal charge can be used to help in the assignment of resonance structure or molecular topology. Formal charge can help in assigning bonding when there are several possibilities. This can eliminate the least likely form when we are considering resonance structures, and in some cases suggest multiple bonds beyond those acquired by the octet rule. It is essential, however, to reminder that formal charge is only a tool for assigning Lewis structure, not a measure of any actual charge on the atoms. Formal charge is the apparent electronic charge of each atom in a molecule based on electron dot structure. Formal charge on an atom is the number of valence electron available in free atom of an element minus the total for that atom in a molecule, determined by counting lone pair as 2 electrons and bonding pairs as 1 assigned to each atom. In case of polyatomic ions, the net charge is perceived by an ion as a whole, not by a particular atom. However, some purpose each atom in a polyatomic ion or molecule is assigned as a formal charge. It is defined as the difference between the number of valence electron in an isolated atom, that is the free state, and the number of electrons assigned to that atom in a Lewis structure. The counting of free electron based on the assumption that the atom in a molecule own 1 electron of each shared pair and both electron of a lone pair. Formula of formal charge: number of valence electron in free atom of the element minus number of unshared pair, that is the lone paired electron on the atom, minus half into number of bond pair, that is the shared paired electron to the atom. This is the common example O3. Lewis structure of O3 means ozone gives air, and numbering each atom 1, 2, 3. Formal charge of O1 equals to 6 minus 4 plus half into 4 equals to 6 minus 6 equals to 0, and formal charge of O2 equals to 6 minus 2 plus half into 6 equals to 6 minus 5 equals to plus 1. Formal charge of O3 equals to 6 minus 6 plus half into 2 equals to 6 minus 7 equals to minus 1. I think you are enjoying to watch my video. I think you are understanding all the points. If are not clear, so comment me and I will be replied you. If you are need to discuss any topics, please comment me. I will be discussing for you. So thank you everyone. Bye bye.